Well, hello. Let's do entropy, shall we? Disorder. So basically craziness. Okay, disorder. So for example, this video in itself is a bit disordered because I'm moving all over the place. Oh, I'm off. I'm on again. Okay, all over the place. Chaos, entropy. Okay, that's all that is. So let's go and talk about entropy in terms of chemistry. So here we have entropy, measure of dispersal of energy in a system, basically chaos. So it's chaos. So when we talk about that, the greater the entropy, the more disordered the system. So those words, the more disordered, that's what you need to put in the exam. That's what you need to focus on, okay? The more disordered the system. So if we look at this one, okay, a very ordered system. We look at this one, a more disordered system. Okay, so this is disordered, a bit all over the place. Got a bit of order to it, but not much. And we'll go through the different examples of, in terms of chemistry, what is the disorder and what is the more ordered, okay? And explain how you need to do that in the exam, okay? So why do chemical reactions happen? Now, chemical reactions happen because there's enough energy to make them happen. But there's two things that it really depends on, okay? Now, exothermic reactions have activation energy here, okay? And the activation energy has to be put in to make it happen, and then you lose energy, and then this energy here in the reaction then gets given out to the surroundings, which then supplies activation energy for another one to happen. Now, how does this energy get calculated, get determined and everything? It's really to do with two different systems. Now, the two different systems, one of them is entropy. So reactions tend to favour an increase in entropy, okay? And so basically you'll find that, and we'll talk about it later, there's something called delta G that is dependent on entropy. And so in this case, for example, if you look here, we've got an increase in entropy. So we've got H2O2 here going to water and gas. So gas is more random than a liquid. Okay, and also there's 3 moles on this side and 2 moles on this side. So this is definitely a more disordered system. Okay, so this reaction is favoured because of that favourable increase in entropy, in chaos. Now, if we then move on to some further examples about why they happen, okay, sometimes a reaction will not happen no matter how much you heat it. That means that the activation energy cannot be the only important thing, okay? So that's when your entropy comes in. So we need to look at a balance between an increase in entropy and other factors, including the temperature, including the overall change of the reaction itself, with the exo or endo. And we can determine the feasibility of this with something called Gibbs free energy. Gibbs free energy is equal to delta H minus T delta S. There's another video on Gibbs free energy, okay? So don't think you have to go too much into it now, but we will describe the different parts of it. So the different parts of it is delta G is Gibbs free energy. We've got delta H, which is the enthalpy change, T, which is the temperature in Kelvin, and then the change in entropy is S. Okay, so in your course, you're only going to have to do with the change of entropy. In other courses, it can be slightly different. We're just going to have to do in this course the change in entropy only. So that means the entropy of the products minus the entropy of the reactants. Okay, you can see lots of different versions. We're only going to do that version. Now, in the next video, we'll talk about delta G and how to calculate this and what that means. So in the next video, we'll tell you, and we'll tell you now, that delta G, if it's 0 or negative, means the reaction is feasible. And that means the delta H, the temperature, and the change in entropy are going to affect whether that's 0 or negative, and therefore they all affect whether the reaction is feasible, whether it may happen or not. But we'll do that in the next video. So, determining entropy change. Entropy is the measure of a disorder of a system. We've said that, came in a bit crazy to show a little bit of entropy there. Entropy increases when the energy in a system spreads out or becomes more random. So let's have a look at some of those examples, okay, and the following changes. Heating. Well, that means you're spreading energy, okay? So therefore, that is an increase in entropy. Melting from a solid to a liquid. Well, solids are ordered in nice, ordered parts. So, okay, a liquid is random, moving randomly all over the place. So therefore, that is an increase in entropy. Boiling liquid to a gas. A liquid is more ordered than a gas. A gas is all over the place, floating all around my head, okay? A liquid stuck in its container. Dissolving solid to a liquid. So you take a solid, you put it into a liquid, and it's aqueous. Well, it's more randomly arranged at that point. Effervescence, liquid going to a gas, or a reaction when you're producing a gas is what I'm talking about. Okay, if you produce a gas and it's liquid and solids on the right, the entropy has gone up because you produced a gas. Now, let's predict some changes then, shall we? Okay, we've got this one. This is H2O2 going to 2H2, and this I've already talked about on the board, okay, before, but you can see here, there's two reasons. You've got a liquid going to a gas. So straight away, gas is more randomly dispersed than a liquid. Okay, so I think this is going to have, let's do it over here. Let's do my delta S is going to be a positive. It's going to be getting bigger. My delta S is going to be getting bigger. So if I say positive, it means it's getting bigger. So the delta S of the reactants is going to be less than the delta S of the products. Okay. Right, next one. We've got hydrogen plus oxygen going to H2O. This time we've got two gaseous things going to a liquid thing. Okay. Okay, and also we've got 3 moles on the left going to 2 moles on the right. So 2 moles is going to have a less disorder than 3 moles, and it's going to a liquid, and its gases on the left-hand side. So is that going to be more disorder or less? It's going to be less disorder. So we're going to we think that's going to be a negative delta. So it's going to get more negative. Then go to the next one, and we can say, right, okay, here we have aqueous, aqueous. So the first thing you look at really is the state symbols. Aqueous, 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 liquid, gas. Oh, we got a gas. Okay, we got a gas, which means the entropy is going to go up. Okay, now notice here as well, you've got 1, 2, and then 1, 2, 3. Okay, so the number of molecules you're making or compounds you're making has gone up as well. Okay, and you've gone to a gas. So therefore, that's going to be a positive delta S. Okay. Now, go for the next one. We've got liquid, okay, carbon, solid, okay, and we've got liquid again, and we've got carbon. Now, I know you wouldn't normally see liquid, liquid for iron, but imagine this is very, very hot. That's happening. Very, very, very hot indeed. Okay. And that allows, and you've just got to go off the state symbols that they give you. So if that's a liquid, solid, liquid, gas. Okay, liquid and a solid and liquid and gas. Okay, there's more entropy in the gas. Also, there's 4 moles here, 3 moles there. So there's 7 on this side and there's 5 on that side. So it's definitely going to be an increase in entropy. So we are going to go, let's do our delta S. That's going to be a positive change, okay? Now, next one, magnesium chloride, aqueous, plus a gas, goes to a solid, and aqueous, okay? We have got an increase in entropy in terms of the number of molecules or compounds, so 3 versus 2. Okay, however, we're going from a gas to a solid and aqueous. That's a massive change in entropy, as in it's going down, okay? So there's less disorder. Now, if you then look at this, we'll just do one final one before we go over the whole lot. You can also do it with this example here. Now, these are all gases. And if they're all gases, your one you go to is which is the largest number of moles on which side. So basically, you've got 3 moles that side. Okay. Sorry, there should be 3 moles on that side because we need to balance this down here. So there should be a 2 there. Okay. So 2SO2. Okay. If we do that, and we need also for the O2 here, because it hasn't been balanced, okay, we're going to need to put, there's going to need to be 3 of these. Okay, so 3O2, so 2SO2 and 3O2. Now, what we've got there, okay, is 2 moles on that side and 5 on that side. So the number of moles is going down. So when you've got them all in the same state, it's about the moles. So 3 going to 2, 3 and 2, sorry, 5, 3 plus 2 is 5 going to 2. Okay, so that's going to be a negative change in entropy. Okay, it's going to be less entropy as you go along. Now, if we look at this, and we look at this in terms of favourability of the whole thing, okay, I know this reaction happens very slowly, okay, it happens really, really slowly, okay, and it happens with a tiny bit of light, so it happens with a little bit of light, and that happens slowly. Well, we've got a positive entropy change, so that's good, so it's probably happened, and negative, so that's why it happens, okay, we've got a nice favourable change here, and we'll talk about that in more detail. But I'd rather just shut down here and go to one that we know doesn't work. And we know here, this one doesn't work. Because you know that in class, you add hydrochloric acid to magnesium to make this. You don't go this way around. Okay, so one of the big reasons for that is that it's got an unfavourable entropy change. So it's got an unfavourable entropy change. So this doesn't work, okay? And we'll go into more detail of why that doesn't work in the next video when we do delta G. But you can also see it here, unfavourable entropy change, okay? And that doesn't work at normal temperature and pressure. You have to increase the temperature and you have to add a spark and things like that. You know, it doesn't just work. You need to add some energy in, and then it's exothermic, so it keeps on going. You know this one works, okay? It was a positive entropy change. So it's not always that it will not work with a positive, with a negative entropy change. But most of the time, that has a large effect because it always wants to go to have more entropy than less. Okay, but the most important thing, more than anything else, is that you can identify which change is going to happen. Look at the state symbols. That's most of the time, and then after you've looked at the state symbols, look at the number of moles. Okay. So now we're going to do entropy change and calculate entropy change. And entropy is given the symbol S. Okay, and the change in entropy is delta S. Now, there are lots of different versions of this. Ours is just products minus reactants. So products minus reactant, don't look at the other ones. There are lots of other ones which include the system and the total and all this kind of stuff. No, just products minus reactants. Okay, so we look at the equation here, and we're given an equation every time. And what's important is the balancing in the equation. So there's a 2 there and 2 there. We'll be given the entropy values, okay, and then we have to use the balanced equation, 2 times 131, 2 times 189. Okay, and it goes into this equation here, which is the sum of the products minus the sum of the reactants. So this little symbol here means sum. Okay, so that's when you put in the products, you put 2 times 189, and in the reactants you put 2 times 131 plus the oxygen, which is 205. So really important, take into account the balancing of the equation. That's where most of the problems happen. So delta S is 2 times 189 minus 2 times 131 plus 205, which is minus 89. Now, do a quick check when you do these, because the only problem that you really come across is one or two problems. One, you forget to balance the equation, and two, you might get these numbers the wrong way around. Okay? So there's a quick check. The quick check is look at the reaction and what do you think the entropy will be, the entropy change will be? Well, I've got all gases and there's 3 here and 2 here. So the number of molecules has gone down, which means I'll probably get less entropy, which means I'll get a negative change, okay? So a negative value, right? Because I'm going down in entropy. Well, it says minus 89, so it kind of works. That works. So it's the right way around. If I'd got plus 89, it wouldn't have worked because that says an increase in entropy, and there's no increase in entropy here because we're going from 3 molecules down to 2. Okay, so that's a quick check to do just to make sure that you've got it right. We'll go on to our final example, and our final example is with aluminium, and let's do a prediction to start off with. Remember, to take into account the balancing of the equation. So we've got 3 carbons, 2, 3, okay. We're going from 2 solids to a solid and a gas, which means the entropy should go up. Should go up. So this has got to be a positive number, otherwise I've done it wrong. So stop the video and do it yourself. What are you waiting for? Come on. Okay. Now, anyway, so the video itself, okay, you see here, and we've got our values coming across. All we've done is use the balancing of the equation. Okay, so we've used the balancing of the equation, so 2 times 28, 2 times 28 for the aluminium, 3 times 198, 3 times for the CO, and we've done this and this. Okay, and then we do the reactant, okay, 51 for the aluminium oxide, and then for this carbon, we've got 3 times 6, because there's 3 of them, times the 6 that's there. That should then equal this value, plus 581. Well, it is becoming more has got more entropy, has got more disorder because of the gas. Okay, so that completely makes sense. Okay, so this is how you do entropy. Entropy will be mixed in with delta G, which is the next video. Please like, comment, subscribe, share on social media so people benefit from this video as much as humanly possible. And thank you for watching, and I hope it helped.